Before we begin, let's review the log mean temperature difference method discussed in the previous lecture. This method is easy to use in heat exchanger analysis when the inlet and outlet temperatures of the hot and cold fluids are known or can be determined from an energy balance. The LMTD method is very suitable for determining the size of the heat exchanger to realize prescribed outlet temperatures when the mass flow rates and the inlet and outlet temperatures of the hot and cold fluids are specified. The second kind of problem encountered in heat exchanger analysis is the determination of the heat transfer rate and the outlet temperatures of the hot and cold fluids for prescribed fluid mass flow rates and inlet temperatures when the type and size of heat exchanger are specified. So here the task is to determine the heat transfer performance of a specified heat exchanger or determine if a heat exchanger available in storage will do the job. The LMTD method could still be used for this alternative problem, but the procedure will require tedious iterations, and thus is not very practical. To simplify these types of problems, the effectiveness NTU method was developed. The effectiveness NTU method is based on a dimensionless parameter called the heat transfer effectiveness, epsilon, defined as follows. Epsilon is equal to the actual heat transfer rate divided by the maximum possible heat transfer rate. The actual heat transfer rate in a heat exchanger can be determined from the energy balance on the hot or cold fluids and is expressed by the following expression. Q dot equals C times the temperature difference between the cold in and out, which has to equal CH times the temperature difference between the hot in and out. So in this case, we defined C sub C and C sub H as what's known as the heat capacity rate. So the heat capacity rate is defined as the flow rate times the specific heat. And you have one of those defined for the cold side and for the hot side. So to determine the maximum possible heat transfer rate in a heat exchanger, we first recognize that the maximum temperature difference in a heat exchanger is the difference between the inlet temperatures of the hot and cold fluids. So delta T max is given by the following expression, THN minus T cold N. The heat transfer in a heat exchanger will reach its maximum value in two cases, when the cold fluid is heated to the inlet temperature of the hot fluid, or when the hot fluid is cooled to the inlet temperature of the cold fluid. Therefore, the maximum heat transfer rate is given by the following equation. Q dot max is equal to C min times THN minus T cold N. So here, C min is the smaller value of CH or CC. So let's look at a simple example. So here we have cold water entering a counterflow heat exchanger. So counterflow, you have cold water coming in here and going this way and then out. Then you have hot water coming in from the left, going through and exiting on the right. So cold water enters at 10 degrees C at a rate of 8 kilograms per second, or is heated by a hot water stream that enters the exchanger at 70 degrees C at a rate of 2 kilograms per second. Assuming the specific heat of water to remain constant at 4.18, determine the maximum heat transfer rate and the outlet temperatures of the cold and hot water streams for this limiting case. So here we're given the specific heat for water. The relevant equation is Q dot max is equal to C min times the temperature difference between the hot and cold coming in. So we can determine C sub H and C sub C. So we get C sub H is 8.36, C sub C is 33.4. So the minimum is obviously the C sub H, 8.36. So Q dot max is given by the following equation. So we have THN, which is 70 degrees C, minus T cold N, which is 10 degrees C. So we crunch this in our calculator, we get 502 kilowatts. So this is the maximum possible heat transfer rate in this heat exchanger. It doesn't mean that's the actual value. That means that this is as good as it's ever going to get. This value would be approached in a counterflow heat exchanger with a very large heat transfer surface area. So the maximum temperature difference in this heat exchanger, delta T max, is equal to THN minus T cold N, or 70 minus 10, which is 60 degrees C. So that's important to look at this and think about it. So here, where do you get the 60 at? Well, if it comes in at 70 degrees C, the hot water, and goes through and as it gets cooled, it can't get any cooler than 10 degrees C. And also, as the cold water comes in this side and gains heat, it can't get any warmer than 70 degrees C. So that's an important factor to remember. So the outlet temperatures of this cold and hot streams in this case can be determined from the heat balance equation. We can solve these equations for TC out and TH out. Plug in the 502 kilowatts, the values for the heat rates. We get 25 degrees C for the TC out, and we get 10 degrees C for the TH out. Now this may look, you may wonder, okay, why aren't these equal? Well, they're not equal because they have different mass flow rates. The flow rate of the hot is much slower than the flow rate of the cold.